We saw in our last video that we can find, if a polynomial is completely factored, we can find its zeros, and we can find its x-intercepts, and we can find its y-intercept. And we could plot those points, and that's going to help us graph polynomials. After a polynomial leaves its last x-intercept, we're not really sure what the behavior is going to be in between, if it's going through, or we don't really know how that is going to work. But after the polynomial leaves the last x-intercept, it will either go up forever or down forever to the right, and either up forever or down forever to the left. It can never curve back around, because if it did, it would touch the x-axis again, and we know we don't have any more x-intercepts. So we know it has to just keep going forever in one direction or the other. And we're going to see that there are 4 different things that can happen. 4 different possible left-right end behaviors. And this is after it leaves the last x-intercept. And we'll talk more about how we figure out what happens in between in a minute. So we could have that both ends go up, that both ends go down, or we could have that we're going down to the left and up to the right, or up to the left and down to the right. Those are the 4 different possible things that can happen. We're going to see that we can use the first term, the leading term, the largest exponented term on a polynomial to determine whether it goes up to both sides, down to both sides, down left, up right, or up left, down right. So let's say that we have a quadratic function, x squared plus 3. At this point, you should be able to think about, well, x squared I know is a polynomial, and the coefficient here is positive, so I know it's a parabola that opens upwards. Notice that this is up left on both sides. That's going to serve as our model for any polynomial that goes up to the left on both sides. Notice that my degree here is 2, is an even number. And my coefficient is a positive number. So that's going to be our model for any polynomial that has an even coefficient, an even exponent. So squared to the 4th to the 6th. And this is always the leading term, the term with the highest exponent. And a positive coefficient. So let's think about what would make that graph reflect over. What would make that parabola face downwards? And we know that that is a negative x squared is going to make this entire graph reflect and open downward on both sides. So we still have an even exponent, which means they're both going to go in the same direction. The end behavior is both in the same direction, but now we have a negative coefficient. So that's the one here with an even exponent, means that both ends face in the same direction, but this one is facing downward because it is a negative coefficient. To help you remember this, you can think about what x squared looks like up to both sides. Even exponent, positive coefficient. You can think about what negative x squared looks like. Down to both sides, even exponent, negative coefficient. Let's think about what x cubed looks like. Remember, x cubed looks like this. Down left, up right. That's this case here. Notice we have an odd exponent and a positive coefficient. So x cubed is going to serve as kind of the model for the down left upright. Odd exponent, positive coefficient. And if we look at f of x is equal to negative x cubed, remember that reflects this one, so it's going to reflect in this direction, and we are up left, down right, which is this fourth case, and we have an odd exponent and a negative coefficient. So negative x cubed is going to serve as the model for this one. All right, and we're going to see in our next few examples that we're going to have other behavior in the middle here. It's not going to just connect up. It's going to have up and downs in the middle. We don't know about those yet. We're just talking about the very ends of the graph after it leaves the last x-intercept on the left and the right. Let's see if we can use that left, right, end behavior to graph a polynomial. And I'm going to give you one that's already factored. So the first thing I'd like you to do is think about what your leading term would be. What would the highest term be? And I'm going to find that by multiplying the beginning here, x, and x. X times x is x cubed. So that's my leading term. That's what I'm thinking about when I'm talking about left, right, and behavior in my table here. So I want you to determine the left, right, and behavior based on that table. And just draw your two arrows. Go ahead and do that real quick. And we see that this is an odd exponent, so we know the arrows are going in opposite directions. We have an understood one here, which is positive, so that means it's going to go down left and up right. The next thing I want you to do is go ahead and find the zeros of this polynomial and find the x-intercepts and find the y-intercept. And we learned how to do that in the previous video. So if you have not watched that video and you have questions about this, watch the previous video. But find all of that information And then go ahead and plot your x-intercepts. Go ahead and plot those x-intercepts and the y-intercept, and then turn the video back on. All right, so we look at our factors here. Factor x minus 2 means the 0 is 2. Factor x plus 3 means that the 0 is negative 3. And the factor is x plus 5, so that means my 0 is negative 5. Every one of those is a real number, so I can write them as ordered pairs, points on the graph. 2, 0, negative 3, 0, and negative 5, 0. And notice I have 3 zeros and 3 x-intercepts, which I was thinking I might have at least that many, or no more than that, because of the cube. Now the y-intercept I'm going to get by multiplying all of the constants. I do not have to FOIL this all the way out and find the entire polynomial to find the y-intercept. So I multiply negative 2 times 3 times 5, which is negative 6 times 5, which is negative 30. So that tells me that my y-intercept is 0, negative 30. And if I plot all of those ordered pairs, and I'm not going to use the same scale for my x and y intercepts here. So those are my x and y intercepts. And I know my left, right, and behavior is down, left, and upright. So that means after my furthest left x-intercept, the graph is going to go down forever. And after the furthest right x-intercept, the graph will go up forever. And I'm going to just cross through here, touch negative 30, and then cross back through there. And that is graphing my graph. Okay, I don't know what I just did. There we go. Okay. Notice every time here, I crossed directly through an x-intercept. I went from one side of the graph all the way over to the other side of the graph. And we're going to understand, we're going to learn that I knew I could do that. I knew that the graph was going to cross completely over to the other side because every one of these exponents, or excuse me, every one of these factors was to the first degree. Those ones were not listed. They were understood ones. That's called the multiplicity of the factor. How often, how many times that factor occurs is called its multiplicity. When the multiplicity is 1, we normally don't talk about it. We don't mention it. But let's look about what happens if the multiplicity is more than 1. Let's say we have a function, f of x equals x minus 7 squared times x plus 3. And we want to find the zeros and their multiplicity. In other words, how often multiplicity does that 0 occur? Then we're going to find our x-intercepts. And our y-intercept, we're going to look at our left, right, and behavior. And then we're going to graph it. So I want you to see what you can do here. I want you to find the zeros. Think about what your leading term would be. to do your left, right, and behavior. If the zeros are real numbers, write them as ordered pairs, multiply out your constants, and find your y-intercept. Now be careful here. This factor actually occurs twice. This means x minus 7 times x minus 7. So watch out for that when you do this work. Okay, if I set x minus 7 equal to 0, then my 0 is positive 7. But because of this square, my multiplicity is 2. It occurs twice. And with x plus 3, if I set that equal to 0 and solve for x, my 0 is negative 3. Those are both real numbers, so they give me 2 x-intercepts, negative 3 and 0. If I were to multiply this whole thing out, I would have, my constant would be negative 7 times negative 7 times positive 3. 49 times 3. Let me just do that on my calculator real quick. 147. So my y-intercept is going to be 0, 147. My left, right, and behavior, I have 3 x's here. 2 x's from here and 1 from here. So my leading term is x cubed. So I'm down left, up right. And let's go ahead and graph this. I'm going to plot my x-intercepts. And my y-intercept, and I'm just going to go way up here and say this is 147. And I know I'm going to go down left from the furthest left one and up right from the furthest right one. All right. The behavior of the graph is going to be different at this x-intercept because of the multiplicity 2. 2 is an even number. If we have even multiplicity, then that means that the graph is going to touch at the x-axis and then turn straight back. That's called tangent. We'll have tangent behavior. It'll touch and go back, either from the bottom or from the top. If we have odd multiplicity, which is what we've looked at in all of our previous examples, it's going to cross from one side to the other, either from the underneath to the top or from the top underneath. So let's look at what we have here. Negative 3 has multiplicity 1. We don't write that down. It's understood. Multiplicity 1. 1 is an odd number. So at negative 3, it crosses over, and that's good because it has to go up here and hit 147, and then it comes back down. And notice at 7, we have multiplicity 2. 2 is an even number, so we know the graph is going to touch and go straight back and be tangent at at 7 because of the even multiplicity. And here we crossed because of our odd multiplicity. In our next video, we're going to kind of pull this all together, look at left, right, and behavior, x and y intercepts, cross or tangent behavior for multiplicity, and we're also going to look at a method of factoring a polynomial